to construct zero energy new buildings by 2020, renovation targets should aim to transform existing buildings into nearly zero energy buildings too. iNSPiRe has set its sights on finding solutions to help meet the EU's energy consumption reduction goals in existing building stock across Europe. The key objective of iNSPiRe is to tackle the problem of high energy consumption by producing systemic renovation packages that can be applied to the residential and office buildings. The renovation packages developed by iNSPiRe aim to reduce the primary energy consumption of buildings to lower than 50 kilowatt hours per metre squared per year. The packages need to be suitable for a variety of climates while ensuring that optimum comfort for the building users is achieved. Essentially, the initial stage of iNSPiRe is the analysis of the building stock across Europe to produce a number of target examples that represent the majority. By looking at these buildings holistically, taking in all aspects of structure and energy distribution, iNSPiRe will use these templates to consider renovation procedures. Simulation data will also be used to build a database that will be used to help when making renovation decisions. A major stage in the iNSPiRe project will be the development of multifunctional renovation kits. So how will this be done? The how. The pieces shown here: energy saving technology, innovative energy generation and distribution systems, lighting systems, renewable sources, viability, monitoring, industrial scale value, and business plan for market will be thought through and applied to inform and help develop retrofitting packages, and will be integrated into the building envelope and be made ready for market. The 4-year project entails 9 work packages in total. Work package 9, which is led by EURAC, is the management work package of iNSPiRe and is responsible for the coordination of all partners within the project. Work package 9 is the dissemination, training and social awareness aspect of the project, which is led by Insight Publishers. The work packages are all linked and the information and outcomes feed directly from one to another. I will now quickly provide some details of the work involved in the various work packages. The work in Work Package 2 lay the foundations of iNSPiRe with an assessment and categorisation of the building stock, both residential and offices, across the EU 27 countries. This is important because we need to know what we are dealing with before we think about what and how to renovate. This classification process takes in account things like age of the building, structural characteristics, ownership, energy uses, including electricity, heating, also user patterns and comfort requirements, and building regulations and policies. This profiling process leads to the identification of primary types of target buildings. These target buildings will be the ones that will have the greatest requirement for renovation packages. Work Package 2 also assesses the climatic conditions and the renewable energy source availability and uses simulation modelling, which I will come on to later. Work Package 3 is concerned with the development of the envelope packages for the retrofit of existing buildings. Work Package 3 will produce 5 to 10 standardised envelope packages for the primary target buildings. It will produce facade kits, including metal and glass for office buildings and wooden facades for domestic purposes. The facade features different solutions that include the integration of HVAC, heating, cooling, ventilation systems, and the integration of thermal and energy storage systems. There will be 2 roof solutions developed. One will integrate cabling and distribution systems for water, and the second will feature an innovative solar cooling system. This work package will also see the development of an innovative energy generation component, the micropump. Work Package 4 has two objectives. The first is to define standardised energy generation packages and energy distribution packages, and the second is to design industrialised kits for the quick and cost-effective installation of energy generation and distribution technologies as part of the renovation of buildings. The partners in Work Package 4 will design and test at least 5 standardised energy generation packages, 4 energy distribution packages, 1 industrialised modular generation kit and 2 modular distribution kits. The energy generation solutions developed will enable the interconnection of different sources of energy. This work package will also involve the design and development of lighting systems. Work Package 5 will provide the IT solutions across the work packages in iNSPiRe. The primary objective is to define and design a monitoring system to assess the energy savings and performance of buildings under renovation and to build surveillance software that will handle the information produced by a building's monitoring system. IT solutions for monitoring and surveillance of 3 case study buildings will also be provided. Work Package 6 is essentially the hub of all information generated by the preceding work packages. All data gathered from Work Package 2 and the industrialised solution designed in Work Package 3 and 4 will be summarised to develop the systemic renovation packages for both residential and office buildings in order to define a process for renovation. The main outcomes expected from this work package is the database, which I mentioned earlier, a database of performance from an energy perspective of the packages and technologies working together. This holistic tool will summarise all the outcomes of the numerical simulations with performance figures from the varying aspects of the renovation packages. The database will be organised in an accessible way in order to serve professionals in the engineering and architectural sectors as well as local authorities and decision makers. The purpose of this database will be to inform them of the most efficient and cost-effective means of deep renovation of buildings. This work package also covers life cycle analysis and life cycle costing. Work Package 7 is the case study stage where the developed approaches, tools and technologies will be applied to real buildings, monitored and assessed. The objective here is to demonstrate the effectiveness of the packages developed. There are 3 chosen demo sites. The Ludwigsburg one in Germany, which is an example of social housing built in the 1970s. It contains 3 flats on 3 stories, and during the renovation process a wooden facade and a roof will be fitted onto the building. The second is Madrid in Spain. This site is another example of social housing, this time from the 1950s. This site is 5 stories high and will also be fitted with a wooden facade and roof. The last one is Verona in Italy, which is an office area of a factory. This building has 2 stories and 200 metres squared of facade will be fitted onto the front. Before the renovation process takes place, an energy audit will has to take place in order to understand the performance baseline of the demo sites. The sites will then be installed with industrialised kits, distribution systems and energy management systems. The site will be constantly monitored and this will continue for 1 year. The criteria on which the buildings will be assessed are energy, environmental, financial and user comfort. And the last work package is Work Package 8, which will focus on the analysis of road to market for the industrialised kits and models produced during the iNSPiRe project. Using customer acceptance as the guiding principle, the process of analysis will cover the industrialisation process, installation issues, business models, market introduction and non-technical barriers to large-scale implementation of these packages. It will focus on logistics and installation and take into account transportation, storage, the plug-and-play potential of facade solutions, as well as considerations around insurance and potential level of disruption to the building occupants. It will also cover non-technical barriers, and standards, quality assurance and certification for the packages will also be defined. The 6 kits developed are listed here. If you would like to know more information, more technical details about these, then please email me and I will put you in contact with the relevant partner. So how are BSRIA involved? Well, we're work package leaders for work package 2. As I mentioned earlier, before we can develop renovation packages, it is important to get a good understanding of what the challenge is. What does the current stock look like? How many buildings are there? What condition are they in? What is the typical in terms of typology and also construction? In order to understand this, we have undertaken a building stock survey and analysis covering both residential and office buildings, and this has been carried out separately for each of the 27 countries. The survey and literature review collected information about and data about the number of existing buildings, floor area, age distribution of the stock, construction types, U values for walls, windows and roof, and typical energy consumption and demands for things like space heating, domestic hot water, cooling and lighting. A range of sources were used to obtain the data, which enabled us to carry out a validation process. Along with URAC, we also created a database to hold all the statistics in, so appropriate averages could be derived, and so total energy consumption at EU level could also be determined. The process enabled us to identify typical buildings in Europe and those in need of energy efficiency upgrades. These then became the representative target buildings. We have also reviewed policies relating to renovation, incentives and regulations in each country as part of our survey. To help with the comparisons, as part of our analysis, we grouped the EU countries into these 7 climatic regions. So what did the research tell us? Well, for the residential building stock, we know that post-1945 there was an urgent need to build quickly and cost effectively. This resulted in energy inefficient homes. Standardised methods were introduced in the 1950s. During the 50s and 60s, industrialised, prefabricated and composite construction methods were used to reduce the construction costs. Prior to the 1970s, there was a lack of insulation in homes, and then the energy crisis hit during the 1970s. This then led to an increase in energy efficiency and quality of housing, and we started to see the introduction of insulation in homes. Since the 1970s, and particularly post-1990s, there has been increasing demand for improved energy efficiency in buildings, which has been more recently driven by the introduction and tightening of regulations. So we started collecting information on the amount of residential floor area in each of the countries. And what we found was that actually 72% of the total floor area actually lies in the 6 most populated countries: UK, France, Germany, Italy, Spain and Poland. Then, to get an idea of the state of the stock, we looked at the age distribution by country. Here you can see those countries with older stock, such as UK and Sweden, and those with a relatively young stock, such as Spain. 54% of the residential stock within the EU by floor area was actually built pre-1990, which kind of gives you a scale of the problem that we face. Then, by collecting U-value data, so this gives us an idea of the thermal performance, which was mostly done according to the age and the building element, so we've got walls, windows, floors and roof, we could get a better idea of the state of the current stock. This correlated with the building standards and regulations, helped us to get a better idea and better understanding of when improvements were made in terms of the construction methods. The thermal performance of the building elements has improved in all EU 27 countries since 1945, with the most dramatic improvements generally happening since 2000. Clearly, some countries that are in the coldest climates have always had good thermal insulation, and countries in the hottest climates used to have poor thermal insulation. In terms of targeting fabric retrofit measures, older dwellings give more potential for improvement. The survey also allowed us to build up a picture of the typology within each country. The residential mix between single-family houses and multi-family houses differs widely between the EU 27 countries. Denmark, Ireland, Netherlands and UK have the highest proportions of single-family houses, whereas places like Estonia, Italy, Latvia and Spain have the lowest proportions. In terms of the construction types and materials, single-family houses were dominated by masonry construction, either solid wall or cavity wall. And in multi-family houses, we see that masonry and concrete for low-rise and for pre-1960s. And then for 1960s onwards, we start to see more skeleton frames, mostly reinforced concrete. In the residential sector, the single-family houses represent the majority of the heated floor area. This means that to be effective across the whole residential stock, retrofit solutions need to be designed to accommodate both single and multi-family homes. Using all the information collected, we were able to build up a picture of the EU stock and identified a number of target buildings. These were generally the buildings typical in the key countries in the key years needing energy efficiency upgrades, i.e. those pre-1970. So the three categories we came up with were the pre-1970s masonry construction. These were single-family houses with no insulation, and they were typically 2 stories high, covering an area of less than 100 metres squared. The second category was a concrete framed multi-family homes. This would have concrete or prefabricated concrete facade, and it was typical of the 1950s to 1970s. And the third category was a masonry construction or concrete frame with a non-insulated masonry facade, which was typical in the 1960s of multi-family homes. If we move on to the office stock, the availability and the detail of the data relating to the office building stock was very limited and in many ways more challenging than the residential. The reason for the limited availability is that there is generally no systematic way in place for collecting data on office buildings, particularly those that were built pre-2000. The total office floor for the EU 27 is estimated to be around 1.2 billion metres squared. Over 70% of this total office floor space is populated in these 6 key countries again. In terms of ownership, the key stakeholders were the private owners, and what we found was approximately 43% of the office buildings by floor space was actually built pre-1970, 14% during the 70s, 13% during the 80s, 16% during the 90s, and 14% after 2000. The 1960 to 1980 period seems to be a time when the office building construction accelerated, and in many countries there is around a quarter of the stock by number of buildings that was built during this time. Similar to the domestic sector, we conducted an in-depth country-by-country survey. Here shows the estimated total floor area in each of the EU 27 countries. And as you can see, the 71% of the total office stock, again, lies in these big 6 countries. So what we found from the office building survey? Well, the data suggests that the building stock built pre-1980 would benefit the most from energy efficiency upgrades, as before this date there were limited energy efficiency requirements, and most countries only started to introduce regulations during the 70s or afterwards. There are lots of different types of offices and they come in different sizes. However, similar offices are seen across many of the countries. Again, similar to the residential, thermal performance in terms of U values have improved, and non-insulated constructions are often found in those built in 1980. The northern climates of Europe have generally better U values, which is again driven by the cooler climates and earlier introduction and tighter requirements for energy efficiency. With the exception of major cities across Europe, most of the offices are low to medium rise, with the average number of stories being approximately 4. The methods of construction found in the office building stock are some ways comparable to those in the residential buildings. However, it appears that non-residential buildings generally have poorer thermal quality than residential, principally because of a lack of incentives. The data collected shows that overall the dominant structural material of the building stock across Europe is reinforced concrete. The older buildings, i.e. those built pre-1960s, were generally solid construction with vertical load-bearing walls of masonry. Between the 1960s and 1990, reinforced concrete walls and concrete slabs were the most typical during this time. After 1990, steel construction became more common, and then curtain wall facades started to become popular during the 1960s and then have probably been the most popular and typical facade type since. However, it's important to note that many of our offices are actually built of composite facade systems. So using this office information that we collected, we again identified 3 target office buildings. These are broad categories but are typical across Europe and mostly cover those pre-1980 buildings that consume lots of energy. So first category is a low-rise masonry style office building with a brick facade, typical between the 1945 and 1970s. Second category is a skeleton construction type, so reinforced concrete frame with concrete panels, and these were seen during the 1960s and 1970s. And then the third one is a skeleton load-bearing structure, either concrete or steel, with a curtain wall type facade, either metal or glazed. And these were typically built between the 1960 and 1980. As with any extensive research project like this, there is always going to be some gaps in the surveys. But what iNSPiRe has done in Work Package 2 is use simulation methods to fill in the gaps in the energy use and demands by using reference buildings to model performance for a given building in a given climate of a given age, typology and floor area. This was then scaled up to provide a picture at EU of the estimated current performance for EU 27. This was led by our partners CERC. So we are now almost halfway through the 4-year project, and the partners are all busy continuing with the development, testing and monitoring of the renovation kits, and the development of the database and the performance and cost outcomes that are going to be used to make the comparative renovation decisions too. If you want to know more about the project, then please contact me or visit the iNSPiRe website. The URL is shown here. And you can also follow the iNSPiRe project on Twitter and keep up to date with our regular newsletters. So the iNSPiRe project will continue for another 2 years, but hopefully this has provided you with an overview of the project and the work involved. Thank you very much for listening today. Do you have any questions?